Let's review the IPsec concepts, and we're going to start by looking at the Cisco video that's embedded inside of the module.
Internet Protocol Security, or IPsec. If we start with its history, we can see that the internet was not designed with security in mind. At that time, it was a private controlled environment. It wasn't the giant public internetwork of things that it is today. TCP/IP wasn't designed with embedded security as a foremost concern, because at that time it wasn't envisioned as to what it would become. Security, when it was implemented at higher layers, like SSL or Secure Socket Layer for HTTP and FTP, and Secure Shell for remote command line interface connections. But what about other applications that needed to be secured or need security? IPsec was designed to solve this problem, to implement security for IPv4 and IPv6 at the internet layer, therefore securing all of the applications and protocols in the upper layers above it. IPsec provides us with some basic things that are needed in security. One, authentication for data origin, being able to authenticate that your data came from where you think it came from, integrity, that it wasn't changed en route, and protection against replay attacks if the information or the data was intercepted, like in a man-in-the-middle attack. AH, or Authentication Header, can provide those things through IPsec. IPsec also provides encryption for data confidentiality, for keeping our data private, as well as authentication with integrity checks and protection against replay attacks. ESP, or Encapsulating Security Payload, can provide us with those things. That's also part of IPsec. IPsec also provides us with negotiation of security associations and keys through ISACAMP, IKE, and Diffie-Hellman, or DH. IPsec has two modes, transport mode or tunnel mode. Tunnel mode is what's used in VPN tunnels. IPsec can be implemented in the kernel of the and tunnels. IPsec can be implemented in the kernel of the operating system, or it could be added to the stack. This is more typical. You have the application layer, which is in software, the transport layer, where we have TCP and UDP, that's in software, and the internet layer, or IP layer, which also exists in software. IPsec is added at the internet or IP layer and is implemented in software. In comparison to the network access layer, where we have the data link layer and the physical layer, which is implemented in hardware. When we use IPsec and have it added to the stack in an end device, it's called a bump in the stack. When IPsec is added to a network device, like a router, it's called a bump in the wire. In this slide, you have all of the protocols used in IPsec. IPsec is more of a suite or framework of protocols and security technologies than anything else. Let's take a look at the main protocols. The main protocols are AH, ESP, SA, and IKE. Now, AH, or Authentication Header, is more of a header than a standalone protocol, and it's waning in popularity because although it can provide the ability to authenticate data origin, that the data is from where you think it's from, as well as the integrity of the data, that it wasn't changed en route, it doesn't provide confidentiality or encryption. Authentication Header also doesn't work with NAT firewalls. It can't traverse network address translation. Encapsulating Security Payload, or ESP, does provide confidentiality through encryption, and it can provide some of the same authentication methods like integrity checks to be able to verify the integrity of the data. ESP is more popular because of those reasons. Now, security associations are used to set up basically a contract or a recipe for how security is going to be handled from each device or from each end of the IPsec connection or tunnel. Now, security associations are built on IKE, or the Internet Key Exchange, and IKE uses the policies laid out in ISACAMP to set up these security associations. Now, there are two phases in IPsec. There's the Phase 1 Security Association and the Phase 2 Security Association. Phase 1 is used for management and Phase 2 is used for data. Phase 1 creates the policy set and Phase 2 creates the transform set. There's a single policy set used for management in Phase 1, and there are two, one inbound and one outbound, transform sets used for data. Now, all of the things that are set up in these two phases in these security associations are basically all of the security methods we're going to be using. So in Phase 1, what's negotiated is the policy set, and there we lay out the encryption that's going to be used. Let's say it's 3DES or AES. The hashing that's going to be used, either MD5 or SHA with HMAC, which is a keyed hash. The method of authenticating each end of the IPsec tunnel using X509 certificates with either pre-shared keys or public key, and the Diffie-Hellman group that's going to be used to share those keys across the internet. Phase 2 negotiates the transform set. Now, this is used to secure the data. Now, the transform set, we set up the encryption that's going to be used. Let's say we're going to be using ESP with AES encryption and a 256-bit key. And the hashing that'll be used for the integrity check. Let's say we're using ESP with a SHA hash with a keyed hash using HMAC. Those are the basic protocols or the suite of protocols that you'll see in IPsec.
Let's continue our conversation about the IPsec technologies. First of all, remember it is an IETF standard that defines how a VPN can be secured across IP networks. So again, notice it's network traffic, layer 3. IPsec protects and authenticates IP packets between source and destination and provides essential security functions. Now, these security functions should look familiar because they are a review from Module 3. So, confidentiality, it's using encryption algorithms to prevent cyber criminals from reading the packet contents, right? So, looking at the packet and its data. Integrity, it's using hashing algorithms to ensure that the packets have not been altered. So basically what it's doing is it's taking the data and adding a hash to it on one end, and then on the other end it removes the hash and it verifies that we've got the same amount of data. And then origin authentication, it's going to use the IKE protocol to authenticate the source and the destination. So really that's one of the first steps. It authenticates the source and the destination before sending information over. And Diffie-Hellman, the algorithm used to do the secure key exchange over a public network. So IPsec VPNs, remember, this is a layer 3 protocol, okay? It's layer 3 technology. Information from the private network is securely transported over a public network, so it's going through the cloud, right? We're not using any real layer 2 connections, so no PPEP, we don't have to worry about that. And let's see, to remain private, the traffic gets encrypted. So let's just take a look at this. So IPsec is not bound by any specific rules to secure communication. And what that's basically saying is this is what the framework of IPsec is. Then I can choose whatever IPsec protocol I want and plug it in here. Same with confidentiality. I can choose any type of software feature that I want to add confidentiality. All right, so I build the framework to look the way that I want. So what kind of hashing do I want for integrity? Do I want to use MD5 or do I want to use SHA? So IPsec can easily integrate new security technologies without updating the existing IPsec standards. So let's say SHA comes out with a new version of SHA. No big deal, we just add it. And if I want to switch out the existing SHA, I can pull that out and plug a new one in. So the open slots in this framework can be filled with any choice that's available. So like, let's take a look here. Right, so here I could plug in that we're going to use ESP, which is the preferred format. Right, AES, same thing goes there. It's better to use AES than DES or 3DES. Now I could also opt not to use anything for confidentiality. And then integrity, do I want to use MD5 or SHA? Let's use SHA. PSK or RSA? Let's use RSA. And what version of the Diffie-Hellman algorithm will I use? We'll use DH2. Okay. So now we don't typically use ESP plus AH, and the reason is because in an IPv4 network that's going across from a private network to a public network, we have to use NAT. And NAT does not work with ESP plus AH. So let's just review. IPsec protocol encrypts the layer 3 packet, right? Confidentiality, that's ensuring confidentiality of the layer 3 data, right? What's within the packet. And then the integrity, we're ensuring that the data arrives unchanged. Did I send whatever, 64,000 kilobits? 64,000 kilobits get to the other side. Authentication. Let's see. So we're authenticating just like what we're used to. We have usernames, passwords, maybe we're sharing keys. And then finally, what algorithm is responsible for the public key exchange? So this is a way to exchange keys over a public network in a private way. So with IPsec, we get this flexibility because I can switch these around and I can create a custom IPsec framework. Okay. What I have here now is I have set up this custom IPsec framework. Okay, and this is called an IPsec security association. So whatever I have put into the framework is associated with each other for my network. Okay, so the security association is the basic building block of IPsec. And when the VPN is established, each peer on either side is running a security association. And the security associations have to match. Okay, so I've got to have the same thing to negotiate the key exchange on the source and the destination. I have to establish a shared key using the same type of protocol or technology. I need to authenticate, and that information has to be the same on each side. This is the username that I'm using. That's on the destination. This is the username I'm receiving and using. And then we're going to be negotiating the the encryption parameters as well. So notice that I don't have to have a confidentiality encryption. We can just send it over in plain text, hope for the best. So initially what we're going to do here is we've got to start out with IPsec, VPN, and authenticating my source and destination. The device on the other end of the VPN tunnel must be authenticated before I initiate a communication path, right? So again, remember what we do on one side, we have to do on the other side. I can't use ESP and then AH. I can't use AES and then DES. They need to match. But first of all, before I set up an IPsec tunnel, I've got to authenticate, right? I need to authenticate. So there are two types of peer authentications, PSK and RSA. With PSK, a secret key is shared between the two parties using a secure channel before it needs to be used. So I set up a secure channel, I share the key. Because the channel is secure, no one can gain access to that. I'm using symmetric key cryptographic algorithms, right? So if you need to review the asymmetric and the symmetric, that is in Module 3. A PSK is entered into each peer manually and is used to authenticate the peer. Let's see, IPsec protocol encapsulation. So choosing the IPsec protocol encapsulation is the first building block of the framework, right? So right here, right? And in this case, they have to match, so we're using ESP, okay? IPsec encapsulate packets using the authentication header, not very common. You're almost always going to be using ESP. The choice of AH or ESP establishes which other building blocks are available. AH is appropriate only when confidentiality is not required or permitted. Okay, normally we're going to use ESP. ESP provides both confidentiality and authentication. So IPsec confidentiality. The degree of confidentiality depends on the encryption algorithm and the length of the key used in the encryption algorithm. The number of possibilities to try to hack the key is a function of the length of the key. The shorter the key, the easier it is to break. Right? So here we're using AES, right? And AES and DES both have different key lengths, okay? AES is the preferred. We really do not use DES and 3DES anymore. And you can see why. Because with standard DES, we only have a key length of 56 bits. So that's much easier to unencrypt and to figure out, right? They can get to what that encryption key is. 3DES, it's 56 bits times 3, but the same thing. It's still going to be easier. So with AES, we've extended the length of the key. And then SEAL does a couple of other things. It actually has a cipher as well, which means it encrypts data continuously rather than encrypting blocks of data. And SEAL uses a 160-bit key. This is the preferred method, however, it's very overhead intensive. So typically what we're going to be using is AES. And again, least secure to the most secure. IPsec integrity. The data integrity means that the data has not changed in transit. What I start with from the source is what ends up at the destination. So a hashed message authentication code, HMAC, is a data integrity algorithm that guarantees the integrity of the message using a hash value. So basically, I'm going to take the data, I'm going to add a hash to it, send the data across the tunnel. The hash is removed and calculated based on the hash to verify that nothing with the integrity of the data has changed. MD5 is still pretty common. However, it is not as secure as using SHA because SHA is going to use a 160-bit key, secret key. Let's see. So then we've got the two types of IPsec peer authentication. We have the pre-shared key, PSK, very common. The value is entered into each peer manually. It is easy to configure, but it doesn't scale well, right? So if you need to set up several IPsec tunnels, you are not going to use a PSK. You're going to use RSA because it uses digital certificates. And this is what we are accustomed to using when we're getting software and things like that. Each peer must authenticate its opposite peer before the tunnel is considered secure. Diffie-Hellman is the algorithm that is used that allows the two peers to establish a shared secret key over an insecure channel. So basically over the public network, right? But Diffie-Hellman's algorithm essentially complicates things enough that it cannot be detected or it's not able to be deciphered as it moves across the public network. There's variations of the Diffie-Hellman key exchange, and those are called groups. the higher the group number, I believe the more secure it is. So 1, 2, and 5 we don't use. DH groups 14, 15, and 16 use larger keys, right? 2048, 3072, and 4096 respectively. The Diffie-Hellman groups 19, 20, 21, and 24 have key sizes of 256 bits, 384 bits, 524 bits, 21 bits, excuse me, and 2048 bits, and support elliptical curve cryptography. So this reduces the time needed to generate the keys. We might want to look this up. I believe that because it supports elliptical curve cryptography, even though it's a smaller number of bits, this is considered more secure. Lastly, we're going to take a look at IPsec in transport mode and tunnel mode, and that will close out this module.
In transport mode, there's only the single IPv4 header, which isn't changed. So you have the IPv4 header here, protocol 50, pointing to the fact that we're using ESP, and the ESP header is added. There's also an ESP trailer, and the ESP trailer tells us that the next header to look at is the TCP header in the encrypted IP data. So once this is decrypted, we'll have a TCP header next. Here's the ESP authentication data, and if this option is used with ESP, then we're going to also have authentication, meaning we're going to have an integrity check, or we're going to hash the entire from ESP header to ESP trailer. We're going to hash all these fields so that we can verify the integrity of the data, that it wasn't changed. Now let's compare that to tunnel mode, which is used in VPN tunnels. In this case, the entire original IPv4 entire packet is encapsulated and encrypted. Not only the IPv4 data with TCP header and TCP data, including application layer data, but the original IPv4 header is encrypted along with the ESP trailer. Notice that the ESP trailer says the next header that to point to will be the IPv4 header, because there's an original IPv4 header. There's an IP address, and there's a new outer public IP address over here that was created. The new IPv4 address points to the fact that we're using protocol 50 ESP, and there's the ESP header and ESP trailer and ESP authentication data if we decide to have integrity checks or authenticated information through hashing. This is the type of packet that you would see in an ESP or VPN tunnel, with the original IP address and the new or public outer IP address.